Yeah, camps on everyone. Let's start off. So last class we have finished with surface tension, starting with elasticity. The chapter is not really that tough. It's like it again kind of looks like NLM. If you know how to find tension in a system, 80% of the chapter you know how to do, right? So it is mostly that for different types of systems you should know how to find tension. So let's see what is this elasticity. Now again we go back to the basics. We try to study how does the force between molecules vary. We have done this in thermal expansion. So if you take two molecules, and you know the electrons are spread out everywhere. So here, this is your molecule 1. This is your molecule 2. So the nucleus 1 attract the electrons of molecule 2 and vice versa. This actually results in attraction. In case of gases, this is what we call as van der Waals forces. And this force is attractive in nature. No, but if you push them too close, the nucleus, both are positive charge, will start getting repelled. And force becomes repulsive. Right? So if you try to plot a graph, force versus R graph, where R is the distance between molecules. This is how the graph would look. Now, if I call this point as some R0, and if I call this point as some R1, so R1 is the point where the force is 0. And here this force is repulsive. So positive force is repulsive. Negative force is attractive. So we have done this in thermal expansion, if you remember. So when the molecules are very far, the attraction is almost negligible. As you get closer, force increases to maximum. And then if you push them closer, they start repelling. Now the same graph, if you try to draw, now in chemistry, the similar thing, you would have seen a potential energy versus R graph. U versus R. U is potential energy. Now we know potential energy, the relation between them, F is equal to minus du by dx. So basically when force is zero, the slope is zero. So this graph would have looked like this. So at this point, you should get a minima. And this would be R1. Is that making sense, everyone? So the point where the force is zero, that will be the minima for a potential energy graph. So even though the graphs kind of look the same, the positions where you get the force zero is different. So in chemistry, what you see is the green color graph. It's the same thing, whether you're drawing in terms of FR or you're drawing in terms of, the potential energy versus R graph. Is this basically clear, everyone? So how does this exactly create a problem for us? So that means when these bonds are formed, if you try to push them, so if you take a molecule in a lattice, now it is actually surrounded. There are two more molecules on the front and the back also. So every molecule is attracting here, net force is zero. But now if you displace the molecule, let's say something like this. Now, if you get too close, this guy will start repelling, whereas this guy will attract, attract, and attract. Can you see what happened? The molecule will try to come back to the natural position. So when you molecule is displaced, now the net force will try to restore the molecule. It will try to bring it back to the natural state. The net force will be towards the initial position, or you can say mean position. So this is important. That means whenever a body is deformed, this is what actually happens. If you take a rod and if you try to compress it, it will try to resist you. If you try to stretch it, it will try to resist you. You're getting it? It doesn't matter whether you're trying to stretch a body or whether you're trying to compress a body, the body will always fight back. And this is a reason at a molecular level. So when you take a rod and when you're trying to pull it, right, it will try to pull you back in. If you try to compress it, it will try to push you out again. So this is a reason why a body will always resist deformation. And when I say deformation, it could be compression or elongation. So when a body is deformed, internal restoring forces. Now look at the word internal restoring forces. Internal meaning inside, right? Restoring. These are the forces which will try to bring you back to the natural state. Simply to put it, this is nothing but tension. So the word looks pretty hi-fi, but what we are talking is simply the tension in the rod. So when you say tension in the string, tension in the rod, what you're talking is this is the force which will try to bring you back to the natural state. At least it will fight back. Generated, which try to bring the body to the natural state. This property is called elasticity. So this property of resisting deformation is called elasticity. So most people, right, have this misconception actually. When you say elasticity, they think it will stretch because we start comparing this with the elastic band which we get, like a rubber band or something. So if I ask you this question, which is more elastic, steel or rubber? Again, you need to go back to this thing definition. Now, it's again, like I said, people misuse the word elastic. Tell me one thing: if you have a 1 meter steel wire and then a 1 meter copper, rubber wire, and if I try to pull them both by 1 centimeter, which is more easy, which is more difficult? Pulling a steel wire by 1 centimeter is more difficult than pulling a rubber wire, isn't it? That means steel will resist you more, or steel will try to fight back with you more. So steel is actually more elastic. Rubber is more stretchable. Like I said, somewhere down the line, the word elastic became it can stretch more easily. So that is a wrong misconception. It is like when people say, right, I need to use the restroom, I need to use the washroom, and no one is actually resting in the room, and no one is actually going to wash anything in the room. It looks more posh, right? Because I still remember when we are in school, we used to say, teacher, we need to go to the toilet. Now, if you say, teacher, I need to go to the toilet, people will look at you like, oh, this kid doesn't know English, something of that sort. So it doesn't look that fancy, maybe. So, same way, so words are always messed up that way. So the question is this, which is more elastic? And by the way, this was a PYQ. I think it was a PYQ in CET, I guess. I saw this somewhere. Which is more elastic, steel or rubber? And as usual, everyone wrote rubber in game. So the answer would be steel. Steel is more difficult to deform. So elastic meaning it tells you how difficult it is to resist. There are different types of elasticity, so you just can't compare like that. You can say diamond, right, is also elastic, but it'll break even before anything happens. So steel is more difficult to deform than rubber. Therefore, steel is more elastic. Yeah, generally you can say like that. Anything that is more difficult to deform is more elastic. Yeah, but there is a limit. When you try to stretch certain materials at some point, right, they will start cracking. If you take concrete, when you try to compress it, it will fight back very good. But the same concrete, when you try to stretch it, it will just be torn into pieces. Clear with this? So this is the thing what we call as elasticity. So at a fundamental level, it is the molecules getting deformed and fighting back. That's what we call as elasticity. Okay, someone got disconnected. Okay, clear with this? Next thing. Do you guys remember the word plastic bodies? We have done this in collisions. Anyone remembers? Elastic body, plastic body, we discussed in collisions. So what's a plastic body? So a plastic body is, where the quotient of restitution is zero. Best example, your chapati ka dough. You try to deform it, you push it with your finger and you remove the finger, it doesn't recover at all. Basically, these things have no internal restoring forces. Such kind of bodies are called plastic bodies. They do not resist. Now, other than this, there's also a way to, classify materials. We can say a material is brittle So what I mean by brittle, they're very difficult to stretch, but if you even try to pull more, they'll try to crack. Example, if you take a glass, if you try to take a glass and try to stretch it, they're difficult. But if they stretch even a little amount, they'll start cracking actually instead of actually elongating. These are difficult to stretch and crack. Then we have something called ductile. So ductile, these are they can be stretched easily. So basically, they can be made into thin wires. So these are the kind of materials you use to make electric wires, right? So and can be made into thin wires. Example, copper. Then we also have something called malleability. What is malleability? It can be made into thin sheets. Now, did you see this thing in a Rutherford gold foil experiment? Right? Why did Rutherford use gold? You heard that experiment, right? In a Rutherford gold foil experiment, you take an alpha particles and bombard on a gold foil. Why do you think he used gold? Because he is rich, isn't it? Rutherford is so rich that he wanted to use only gold everywhere, gold spoons, gold, everything. That's what someone said. But yeah, you can see actually gold is pretty malleable. The reason is think about this. If you actually take a thick metal, even though the nucleuses are far apart, if the metal is thick enough, the alpha particles will bombard with some nucleus and will get bounced off. You will get a lot of error in the readings. So you need to make it as thin as possible. Preferably, if you can make it one molecule thickness, that would be ideal situation, isn't it? So it's a little difficult to get a one molecule thickness, but the closest you can get gold, right, is pretty malleable. You can take 1 gram of gold, right, and you can see the room you're sitting in. Look at the floor. You can make a sheet as thin as possible. That big you can make it. 1 gram of gold, and that's what you actually see. Also, ever seen this thing? Sweet is covered by gold foil. People have eaten gold, karke. So it looks like oh they're eating gold, but in reality, a 1 gram gold will cost you around 8,000 rupees or something, 9,000. You can make it into a sheet as big as your room. In that, they'll just cut a piece as thick as your hand ka palm and they cover the sweet with it. You can increase the cost of the sweet from 200 rupees to 500 rupees. It works out. It's still profitable. So what you're actually eating is real gold, but it is so thin in terms of weight, it is nothing. So gold is pretty malleable. Yeah, it's not fake gold. If you actually eat, you can people do sell with real gold also. Clearness? Next thing. So that is one. So that is a little their intro about elasticity and stuff. So we know the fundamentally we know why the materials actually oppose the deformation. Now, if you consider, so whenever you study the materials, you know, the forces and stuff, we need to this thing see. Tomorrow, when you become an mechanical or civil engineer or into robotics or into construction design, anything, the important thing becomes how do you define or how do you judge the strength of materials, isn't it? Tomorrow if you're designing a bike and you want to mount a engine onto the bike, you need to know what kind of forces act on the engine ka frame and how much weight can it take. So mostly you're talking about strength. The problem comes, how do you define that something is strong and something is weak? For example, if you ask you this question, the bones of an elephant, the bones of a rat, which are stronger? If you tell me the bones of an elephant are strong because elephant is big and strong, now you are missing the whole point, right, Surya? Right? Take out your hand from your chin, na? Don't give support. Your body thinks it is time to sleep. So there is a natural thing there. And if you're feeling sleepy, go wash your face and come. That's okay. Wash your face. So again, don't give support with your hand. The thing is, the problem is you're doing a wrong comparison. It's like imagine I have a group of three people, one, two, three, and I have a group of 10 people. And let's say this group of 10 people have a 2 lakh rupees. And this group of three people, right, they have something like 90,000 rupees. Can you tell me which group is rich? And if I tell you which group you want to be, can you see the difference? Overall, when you look at this, it feels like this group has 2 lakh rupees. This is 90,000 rupees. It looks like rich. But you're missing the point. If you see per person, they have 30,000 rupees access. Here, per person is 20,000 rupees access. So even though you will say this thing has more money, you would prefer to be in group one, isn't it? You get anything? So it is not the force that you're looking at. So if you just look at an elephant bone and a rat bone and try to apply the force, yeah, definitely rat bone will break first. But if this was the size of an elephant bone and this was the rat bone, a better thing would be imagine if this guy ka area, again, I'm just giving a number, 2 centimeters square, and let's say it can apply a force of 1,000 newtons. And let's say a rat ka bone is like maybe 0.02 centimeters square, and maybe this can withstand something like 15 newtons. Now, that means if I make this rat ka bone as big as the elephant ka bone into 2 centimeters square, then this can withstand 1500 newtons for the same 2 centimeters square of rat bone. Now, do you really think rat bone is weaker than the elephant thing? So the problem is that you are doing a wrong comparison. If you make the rat as big as an elephant, or if you make the bone of a rat same identical size as an elephant, and then you try to apply the force, and then you'll observe that rat bones are generally more stronger. And when you go at a microscope and actually observe, you'll observe the molecules are more tightly packed, or they might have more calcium, or maybe elephant bone is actually a little more porous. It is more airy, maybe. So the elephant bones are maybe really not that strong. You getting the problem? So whenever you talk about strength, talking about force is a bad idea because that doesn't give you any picture. Meaning, which is stronger, wood or steel? No, you will again, you're getting it again, wrong comparison. So if you compare in terms of force, there is no comparison. What if I take a wood this thick, and what if I take a very thin metal rod? Now, if I try to apply force here and apply force here, won't the metal rod break here? The wood though will withstand, but again, wrong comparison. The areas are not same. So when you want to compare, force is a bad thing. So what we do, we try to compare in terms of something called stress. So whenever you're talking about strength, we don't study force, we study force per unit area. So if you have a body here, let's say we have forces F1, F2, F3, F4, and if you consider an FBD here, cut it here. This will be F3, this will be F4, and on this cross section, you will observe there is a force, tension perpendicular to the surface, and this is a tension parallel to the surface. This is the net tension. So the tension force rate need not be along the area. It can have two components, perpendicular and parallel. This is your restoring force. I'll just write it as this. The restoring force will have two components. So we define something called longitudinal stress. So even in types of stress, there are different types of stress materials undergo. This would be the force perpendicular to the cross-sectional area. Maybe I can just write this as F. And then we have something called shearing stress, which is the force parallel to the cross-sectional area. Getting it? Now be careful here, even though this looks like force per unit area, be careful. This is not pressure, right? This is not pressure. What is pressure? It is a force perpendicular to the surface area. So if you remember this, like I said, the most important thing is per unit area. Meaning, see, we did have a discussion like this once. Is money important? Is money important? So if I say I'll give you 1 crore in 100 years, are you happy? Chalo, I'll give you 1 crore in 10 years. Happy? Maybe 1 crore next week. See, suddenly more happy. So what changed? I'm still not giving you the same 1 crore. But what made you happy when I said I'll give you in 1 week? But when I say in 10 years, you're not that happy about it. So if money was the thing that was really important, you would have been happy anytime. What was more important to you is money per unit time. So what we're looking at is not money, but it is money per unit time. That is a better metric. If someone tells you they're going to give you 10 lakh crores and make you the world's richest person after 500 years, does it matter to you? You will say, what the hell? I won't even be alive within 500 years. So what good is that? Did you see? So it's not the money that you're running behind. Most people don't understand this. What most people are running behind is money, but the actual metric is money per unit time. Getting it? So similarly, when you talk about forces, force is a very bad metric. What you should be studying is force per unit area. That would be a better metric, right? So that is the thing. So have a look at this. So we define something called stress. So instead of talking about force, we talk about force per unit area. That's it. So whenever you think about the right stress, think only about force. There's no difference as such. Clear with this? So there are actually three types of stresses. These are two ones. Any doubt so far? The third type of stress is called a volume stress. We will talk about what is shearing stress and longitudinal stress also. So in the stresses, there are two types. So volume stress is when you have a material and the force is being applied in all directions. So here we define volume stress as force perpendicular to surface area. This is actually pressure. This is the definition of a pressure, force perpendicular to the surface area. So volume stress rate talks about the overall volume compression and stuff. So mostly that's what you're talking about is pressure only, right? So what are these three stresses exactly? So what is longitudinal stress? For example, when you see your building, right, can you see the pillars? What kind of stress do you think the building a pillar is undergoing? You have your building a pillar and the whole weight is pushing down. This is the area and that is the force. So your building a pillars are undergoing longitudinal stress. They're just trying to compress. What about the beams? If you look at a beam in the house, what kind of stress are these undergoing? If you look at here, the weight mg is pulling it down here, and if you look at here, this is the area we're talking, isn't it? So this force is acting parallel to this surface now. This is the shearing stress. So your beams, if you see, they sag actually, meaning the beams, right? Eventually, if you leave them like this, you will see a situation like this. The beams, because of the weight, they do sag. So this force which is there, the force is acting parallel to the surface. It's not perpendicular. The beams undergo shearing stress, whereas your pillars undergo longitudinal stress. That is the reason next time when you observe, when they build any pillars now, observe this thing. They first construct, they put some metal rods, they cover this with a metal wiring, and then they pour concrete inside. But if you take the construction of a beam, you will observe they use double the steel, they use double the metal coverings, and then they pour concrete. Because concrete has a problem. Concrete, when you're compressing, it is as strong as steel. But the moment you take a concrete block and you try to apply force in terms of stretching, concrete will tear into pieces. Concrete is very strong in compression, very bad in elongation. Then why don't we just use steel everywhere? Concrete is cheap. A 1 kg concrete will cost you 5 to 6 rupees. 1 kg steel will cost you 200 rupees, 300 rupees. The steel becomes very expensive. Steel can withstand both longitudinal shearing, it's pretty strong, but you have a problem. So wherever you're pretty sure there is only compression involved, using concrete is the best. And wherever you're sure, boss, यहाँ पे कुछ shearing आएगा, you have to be careful. You have to use more metal there. It becomes expensive. Clear with us? So same way, think about it. When you're standing, right, your legs or your thighs, an adult human being can withstand 1.6 tons, 1600 kgs of force. But did you see normally what people say? My leg got twisted. I got a sprain. My ankle got twisted. People don't say my ankle got broken. People say it got twisted. That is because when you're standing and taking a turn, what are you doing with your body? You're twisting the body, isn't it? You're twisting your leg. That's a shearing stress. When you pinch your sister or brother, you're applying a shearing stress on their skin. Pinching people is shearing stress. Making sense? So you're actually dealing with two different types of stress. So if you're making a robot, right, and when it is just standing, the legs are undergoing, longitudinal stress. But when the robot is trying to take a right turn, left turn on the ankles or the elbows or whatever, there is a twisting torque. You have to design it differently, right? If you don't take that into consideration, it will tear apart. So if you take a paper and if you try to stretch it, let's say if you try to apply force like this, what kind of stress is this? You are applying a force perpendicular to this area. So here its force is perpendicular to area. So stretching a paper is actually longitudinal stress. What if you tear a paper? How do you tear a paper? If you see my screen, when you're tearing the paper, isn't this how you tear? So you're actually applying force on this side, and the force is acting this way, isn't it? It's actually shearing stress. So when you're tearing a paper, you're applying a shearing stress. So you are applying force on this section here, and your force is this way. If you see, it is parallel to the surface. So tearing a paper is actually shearing stress. Did you see your, building ka pillars, and did you see metro ka pillars, which are thick? Metro ka pillars are pretty thick. So you mean to say train is more heavier than your building? Then why do they make the pillars so thick? They're like insanely thick actually. For the comparison, if you just go and look at your 10 floor or 20 floor building, if you're staying in a small building, the pillars will be half the thickness. So what they're trying to fight is not the longitudinal stress. Most people think, our pillars are so thick so that, train ko carry karne. Nah, that's not the problem. There's some other issue there. Look at this thing. If you look at the pillars, the pillar which it is standing and that thing there, the section is like this, isn't it? You have a train going here and you have a train going here like this, front and back. So when this train is going front, how is the friction on the train? Front or back? If the train is going front, what is the direction of friction on the train? Front. Who is making the train go then? Don't forget that when you are walking, friction is in the forward direction. Friction is the one which is making you walk. So friction is forward on the train, the same friction that backward on the section. So what is this friction doing actually? This friction is actually forming a couple. If there are two trains going, they're actually trying to twist the pillar. Every time the train goes over that section, the pillars are getting twisted, isn't it? But if you're building a monorail, you can avoid this. You know why? When you're building a monorail, you will keep the train exactly on top of the pillar, isn't it? Even then, you'll have a slight problem. You're actually twisting the pillar front and back. But generally, elevated these things, they have a very thick pillars. Because this pillar, right, is not being pushed down. That is not the problem. The problem is the pillar is being twisted. And imagine every day you have around 400 to 300 trips train. So each pillar is being twisted 300 to 400 times per day, right? And we are expecting the lifeline of a metro is generally around 50 to 100 years. So they overcompensate it. If you need a radius of 1 meter, they'll try to build at least 2 to 3 meters to be sure for it. So these pillars are built quite thick, mostly right to absorb that twisting torque. Getting it? So metro pillars undergo shearing stress. They have to use a lot of metal inside. Concrete can't withstand this. If you just build a metro pillar with concrete, it will crack in like it won't even withstand an year. You will literally see cracks. So next time observe. Now the moment everywhere they're digging, you can see one metro pillar. You will see there's a lot of metal first of all, a lot of metal, and then concrete is just a filling there. So concrete is will take care of that compression weight, and the metal will take care of that elongation, the shearing stress. Clear with this? Now, different materials will behave differently with different stresses. For example, when you're trying to stretch a paper, is it easy to stretch a paper or tear a paper? You can't stretch a paper that easily. So paper can withstand longitudinal stress. If you try to stretch a paper, it will resist you. But when you try to tear the paper, it just goes off. So different materials will have different kind of limits. Not like if you're strong longitudinal, you should be long in shearing stress also. So people can withstand longitudinal stress, but cannot handle shearing stress. Easy to tear. What if you take a plastic sheet? Did you ever try to open a lace packet or anything, not from the this position, the cover there, but randomly, did you ever try to tear from the middle anywhere? It's very difficult. You just can't tear it. So what you do, sometimes we just put our teeth and then we cut it, right? So if you see a plastic sheet, it is easy to stretch but difficult to tear. So plastic sheet will have less longitudinal stress, but it can withstand more shearing stress. So you should know when you're constructing something what kind of stresses will involve, and accordingly you try to bring those materials. So what about human skin? Isn't it easy to pull your the skin? It will stretch a bit. it is very difficult to tear human skin, right? You can take a pen or something and make holes on the skin, but when you try to pull the skin, it resists it like anything. I'll be showing you some graphical images. This is performed by professionals. Do not try this at home. And no people are harmed in this. Can you see this? This guy is literally hanging with hooks in the skin. They do this thing. Meaning, if you see, even in, I think in Tamil Nadu, I guess, there is this Lord Murugeshan temple or something, some, God ka temple. So there people perform rituals like this. They even put through the cheeks, they make holes, they have skins are tied like this, they do all these kind of things. Now, if you see, right, yeah, it does hurt a bit, but body shuts down the signal after some time. The starting part is painful and then it shuts off. The same way right now, right? Uh, your shirt is touching your skin. Did you see? You just notice that your clothes are touching your skin. But before I told that statement, it is still touching your skin, but you've lost that sensation. So human bodies have that thing. If you continuously send an impulse at one point, after a few times, it will start ignoring it. Right? But when I say your clothes are touching you, suddenly you can feel it, right? My clothes are touching me everywhere. But if I don't remind you, you won't even realize. So it goes off like that. Daksha, bolo na.
Well,
So this image is too graphical, so we'll remove this. But yeah, I don't think you'll try this at home anyways. Daksha.
well, if plastic has higher shearing strength, like capacity and everything, then why don't we like mix plastic with some maybe tough biopolymer or something and make the racks and
They do na. Look at your stools and all, they do that. But problem is with the temperature, right? If the temperature becomes more or something, they do become little soft and all. So you need to take care of that also. And you know how Mumbai temperatures are. One time it is cold, one time it is hot. So
so like
that way.
some hardening substance can't be used.
They do. But end of the day, Daksha, it is all about cost, isn't it?
So plastic is way cheaper than metals, right?
No, it is not about that. When you're doing construction at a large scale, it's a different ball game. People do use plastic in making roads.
Okay.
Uh, but the thing is, you can't use it in bulk. Imagine you make something with plastic and during summer temperature goes to 50 and it becomes little soft. Do you want to take that risk? It's always about that. People wanted, tested and tried methods. No one wants to experiment. We had a professor, an IIT civil guy. This guy is like pretty famous for doing all weird stuff. He's famous, in his lab, he used to have a mixer, concrete mixer, which rotates 24 into 7. Right? What he does one day, he goes there, throws anything inside. He throws rubber pieces one day with concrete, one day pencils with concrete. He does any nonsense. And after that, whatever material comes, he tries to test it and see what can be done. That way, he created something called a liquid concrete. This concrete literally flows like a liquid, right? And when you just pour it there, and within maybe few minutes, it becomes pretty hard, right? So what is the use of this? Imagine you have a wall here and it got cracked like this. Now, if you try to put cement into this gaps, there is no guarantee cement will go till the last gap, right? So, I mean, imagine the cut is something like this. It's this sort. How will you fill up this gap with a normal cement? It's difficult. You can just put something here and pour liquid concrete. It fills up this entire space. It's pretty easy. It flows easily, right? He tested it. It worked pretty well. It had a pretty resilience. All experiments were done. And then we are actually approached, L&T approached big companies, construction companies, and he showed them the project. This is called liquid concrete. I made this, that, this. But everyone said, sir, we understand. You must have tested it also. It works great and all, but we don't want to take a risk. This guy tried a lot trying to sell it, but no one agreed. Finally, got pissed off one day. He built his own house of 3 floors with pure liquid concrete. And then whenever he goes to a company, right, he shows them his house and says, "This is the house where I stay, my kids stay, my grandson stays." That is the kind of trust that I have in the thing that I made, and I'm staying in this house for 5 years. You tell me, you say something like that in front of a company. What will the company say? This is the product that I have confidence in. 5 years I'm staying under the same roof built by me, my grandson, my son, everyone stays here. He was crazy guy. But hey, IIT Madras also, right? They used it to build the entire upper roofing of a hall. So he did got few projects and it did have some success. So it's like that. Just because your product is really good doesn't mean people will use it. End of the day, it is always about effectiveness. People don't want to get into new methods. You have to train new people. It becomes more expensive. That is the reason people think Elon Musk is an. He used to think at least he was an idiot when he said, "I'm going to launch at 1/10 of the cost." He did it in 1/10 of a cost. So we define this longitudinal stress, which is what tension. People do use. Check it out. Construction of use of plastic polymers. करके. They actually use it in roads. It actually makes the roads better waterproof. Mumbai mein we should definitely use this. Monsoon comes, the road is gone next day. So Mumbai mein is another problem. If you build better roads, it becomes problem, to steal money from BMC. Most people think BMC is corrupted and everything. They pay bribes, and they don't bribe. They don't pay bribes. So if I'm the MLA of a local region, what I do? If you're my relative, I'll give you my contract, right? For the entire road of, let's say, for 10-kilometer road, I'll give you a contract. You build the road decent and nice, and whenever there's a small accident, something, every 2 months there is a hole on the road. Something or other keeps happening. You get a call, you come and repair it immediately. People are happy. देखो problem आया, immediately आके repair किया. Every time you repair that hole, I charge you 4 lakhs. Cost of the road 20 crores. Repair of the road in 5 years 50 crores. That is how they steal money, right? So something of that sort. Technically speaking, they should build cement roads. These things have a lifespan of 10 to 15 years. So if you apply force F and F, so this, what is the tension here, anyone? If you pull a rod with a force F and F, what's the tension here? Anyone remember? Tension here will be F. So this is called an elongative stress. Suppose if you're pushing here, this is a compressive stress. Compressive longitudinal stress. So we also define something called longitudinal strain. Which is delta L by L. Same thing again. If I ask you, uh, this body stretches better than that body, now that's a problem again. It's like, tell me one thing. If I have 1 kilometer steel wire and if I have 1 centimeter rubber cord, if I need to stretch this 1 kilometer wire by 5 centimeters and 1 centimeter by 5 centimeters, which is more difficult? The rubber one, right? Even the rubber generally stretches better because the length is only 1 centimeter and you're trying to make it 5 centimeters. 1 kilometer, 5 centimeters is easy. So again, the comparison is wrong. You don't study elongation, you study elongation per unit length, delta L by L. So keep this word simple thing. Whenever you hear the word stress, it means force. When you hear the word strain, it means elongation. Making sense? Fundamentally, that's what they mean. But studying force per unit area is better. Studying elongation per unit length is better. So everything per unit is a better metric than studying directly the length. So here the delta L is change in length from natural length. That thing is important. We'll get back to this later on. L is your natural length. So here we define so when a material is deformed to an extent up to a limit, we have the longitudinal stress is proportional to longitudinal strain. So the stress is proportional to strain. It's like F is equal to Kx. The more force you apply, the more elongation you get. Up to a limit. We will talk about that later on. If you stretch the material too much, it doesn't behave like a normal wire. The proportionality constant, I will just write it as stress, is given by Y into strain. So we get this Y is called Young's modulus, which is the ratio of stress by strain. This is called Hooke's law. So Hooke's law is a region where it behaves like a spring. So this will be our first numerical there. Have a look at this page. Right. So if I just try to substitute here, so we get Young's modulus Y is stress by strain. What is stress? Tension by area, and strain is delta L by L. There. So this is your formula. Young's modulus will be T L by A delta L. Now for convenience, what will I do? I will write delta L as E. Because later on when we have to integrate, right, D of delta L looks pretty weird. So we write delta L is E, which is elongation or compression. There, this is your first formula there. So Y is equal to T L by A. Y is your Young's modulus, which is ratio of stress by strain. And what is the physical significance? Higher the Young's modulus, more difficult to deform the body. So Young's modulus will tell you how strong the material is. For a rigid body, what is Y ka value? So Y for a rigid body tends to infinity. Getting it? Here L is the length along the tension, or L is the length along the rod. A is area perpendicular to the tension. You can note down this formula. This is what I was saying. If you know how to find tension T here, Y, L, A, everything is going, you can calculate whatever you want. So far you know only two things. What is stress? Force by area. What is along Young's modulus? Tension length by A. Yeah. Let's see a question. We have a cylinder. The solid cylinder. They're coaxial. So this point is x is equal to 0. This point is x is equal to L, and this point x is equal to 2L. So each cylindrical length is L. This radius is R. This radius is 2R. So these are coaxial, means common axis, solid cylinders of density rho. So they're stacked one on another. So plot stress versus x graph. What is stress? Tension by area. So what I'm asking is, I want you to find the stress here, divide by the area. You'll get stress here, then here, then here, then here, then here, then here. Then you have to plot a graph. So you'll get a function there. Are you sure everyone what I'm asking? Plot stress versus x. X is starting from the top. So as you go from the top to the bottom, how will the stress change? How do we do this? Should I show you one? See, the problem here is you can't directly do for x from 0 to 12. Why? At this point, the area is abruptly changing, isn't it? So you need to split the problem into two parts. First thing, let's say take x from top here. So take x between L to 0, means you're talking only the upper part of the cylinder. So if you take only till here, what is the tension at this part? This entire shaded area, isn't it? the tension of this part will be the only the weight of this piece on the top. So tension T will be mg of that shaded part, which is density area pi r square into x into g. So what is stress? Tension by area, which is rho pi r square xg by pi r square rho xg. That was easy. Now second part, x must be between 2L and L. So basically L is a discontinuity. Suddenly the area changes. So now you're taking x from here to here. Means you want to find the tension here. Now how much should you take? Should you take this whole area here? You get in the diagram? Is that making sense, everyone? You should take x from 0 to L and then from L to 2L ka beech mein. So they have to divide the part into two parts. Now what will be the tension here? Now the tension will be the weight of the small cylinder, which is rho pi r square L g. This is the upper cylinder ka total weight plus, if this is L, then this length will be x minus L, because this whole length was L and that whole length was L. Is that making sense, everyone? Sharman? Arush? Adjust your camera a bit, Arush. Can't see you. Surya? Arya? Clear with this? Is the diagram clear? Should I draw a separate diagram for this? I can draw two different diagrams showing, but if you got this, then great. Then what is the mass of this piece? You have to take this section also, which will be rho. Area will be 4 pi r square, and the length will be x minus L into g. Is this clear, everyone? That will be your tension. What is stress? Tension by area. Area is 4 pi r square. Radius is 2r. So if you divide them, you will end up with rho Lg by 4 plus rho x minus L into g. This guy will be rho xg minus 3 rho Lg by 4. This is your stress. If you actually try to plot this graph, stress versus x graph, you will see initially it's a linear function y is equal to kx. It's a line passing through the origin till L. At this point, the stress is rho Lg. Then suddenly, when you go from here to here, area suddenly became 4 times, but the tension remained same. The graph will just collapse here. It will be rho Lg by 4. This is also a straight line. This is how the graph looks, everyone. You have a discontinuity at x is equal to L. The stress suddenly becomes 1/4, isn't it? Think about it. If you are here, what is the stress? Total weight by area. If you go just below this, suddenly the total weight by area becomes 4 times, no? The stress will suddenly drop because the area suddenly become 4 times. Have a look at this. That is how the graph looks, everyone. Two straight lines. The first one passes through the origin and the second one goes from there. Yeah. Next one. We got a rod here. Let's say you are applying a force 3F, F, F, and F. This rod ka length is L, this section ka length is also L, and this section ka length is also L. Y is the Young's modulus and A is the area. Find the elongation in the rod. What is the first thing you need to do? Can you find the tension in the rod? Do you think the tension is same everywhere? How do you find the tension here? How do you find tension at any point? Wherever you want to find tension, just imagine it is cut there. So if you want to find tension here, let's assume it is cut here. Then you get two pieces, left and right. Choose any one piece. I will take the right piece. So this is 3F. Let the tension be T3. Since acceleration is 0, T3 is equal to 3F. Then you want tension here, cut it here. You can take left or right. Again, when you say cut it, it's an imaginary thing. So now this is 3F. This is F, and this is T2. This also acceleration is 0, so T2 is equal to 2F. Then you want tension here, cut it here. This will be T1. I will take the left piece, F, so T1 is equal to F. That means when you take this rod, the tension is not same everywhere. Here the tension T1 is F. Here the tension T2 is 2F. Here the tension T3 is 3F. So each section has a different tension. And we know formula Y is equal to tension length by AE. So elongation is TL by AY. So the first piece ka elongation E1 will be FL by AY. Second piece ka elongation will be 2FL by AY. Third piece ka elongation will be 3FL by AY. So each section will elongate differently. The total elongation will be 6FL by AY. Make sense? So that's what I'm saying. If you know how to find the tension, your job's done. Clear? Next one. Next one. Kritik, clear so far? Arnav, next thing. So we have a hinge here. We have a mass m attached here, and we have a mass 2m attached here. This thing is Young's modulus y, a length L. This is also y, a length L. So basically the length of the rod is 12. Now when you leave this is going to swing like a pendulum. Like this. So gravity is there. You're getting how these pieces are? It's like your barbecue nation may have na, this paneer ka pieces on the barbecue. Kind of like that, two pieces stuck. So M and 2M are connected to a light rod and released from a horizontal position. Find the ratio of elongation in the upper half and the lower half of the rod when the rod becomes vertical. Assume the elongation is much smaller than the length of the rod. I don't want the length of the rod to change, because if this comes here, then this will be 2L plus delta L. You'll get messed up. We don't want to include all that stuff. You can neglect the change in length, but it is there. It's not that straightforward. Any answers? We have done this before. Where you have done this? Do you guys remember this question? What is same for both the particles? They have same omega. Both the particles don't have same speed. They have same angular velocity. They're going with v and 2v. It's a light rod. When a rod rotates, what remains is angle covered is same. So when this guy becomes vertical, they have same omega. So if this guy ka speed is v, which is L omega, this guy ka speed will be 2v, which is 2L omega. Loss in potential energy is gain in kinetic energy. So the first one has lost a potential energy mgl. The second one has lost a 2 mg2l. The gain in kinetic energy is half mv square plus half 2 mv square. We get velocity v is equal to root over 10 gl by 9. That is 5 to 10, and that is 4 plus half plus 4. Yeah, 10 gl by 9. That's the velocity, everyone. Then you want to find the tension. How do you find the tension? We'll draw the FBD. You draw FBD of 2m. What are the forces? Tension T2, your own weight 2 mg. Since you're going in a circle, there'll be also centrifugal force, which is 2m, 2v whole square by 2l. From here, we get tension T2 is equal to 2 mg plus 4 mv square by l. You know, v ka value, substitute here. How much is that? That will be 10 by 9, 40 by 9, 40 plus 18, 58 mg by 9. Then you draw FBD of m. You have T1, you have T2, you have your own weight, and you're going in a circle. You also have centrifugal force mv square by l. Then from here you get T1 is equal to T2 plus mg plus mv square by l. This is 58 mg by 9 plus mg plus mv square by l is 10 mg by 9. That is 68 plus 9, 77 mg by 9. Right? And we know the Young's modulus is equal to tension length by AE. So elongation is proportional to tension. Everything else is constant. So E1 by E2 will be T1 by T2, which is 77 by 58. That's your answer, everyone. Is this clear, everyone? So we have in the formula, what is T?
So T is like the tension acting.
Where?
Sir, on the rod, like, sir, if it's like in an
When?
angle,
Tension when? When you're finding elongation, you're finding elongation when?
But that elongation, it would add up, right?
Tension is acting when?
So throughout the journey, kind of.
No, simple thing. I'm asking you, where are you finding the elongation? At which position are you finding the elongation?
Vertical, right?
So at that, so tension should be taken when?
Yes, sir. But like my doubt was that at any angle, as it slowly goes down, the tension, the forces acting increase. So it'll keep increasing
Okay,
the.
fine. Na? So let it increase. So this is the final elongation. What is the problem?
Wouldn't it be larger because we're not taking into account the remaining parts elongation?
So if I give you 1 rupee now, I'll give you 1 rupee later. If I give you 1 rupee later, if I give you 1 rupee later, right? I give you 1 rupee. How much you have? 1 rupee. I'll give you one more rupee. How much you have? 2 rupees. If
To
I give you one more rupees, how much you have? 3 rupees. I'll give you one more rupee. How much you have? 4 rupees. So how much money you have? 1 plus 2 plus 3, 10 rupees you have. Is that what you're saying?
yes,
Vihan has created a way to become rich. How much
oh,
did I give you, Vihan, till now?
4 rupees.
Clear?
Yes.
Hmm. Take a break. Come back by 7:4. Continue from here. Have a look at this. This question is actually work per energy, circular motion, FBDs. Once you got the tension, did you see actual elasticity? How much is there? E is proportional to T. There is nothing there. And this is what I was saying. You know how to find tension. The questions will be quite easy to do. Go, take a break. Come back in 10 minutes. Any doubt so far? Anything that you're not clear, ask. Okay. Let's see the next one. So we got a wire here between two walls. And between two walls. So Young's modulus is Y, area is A, length is L. Then what you did, you suspended a mass M at the center. You took a hook here and you attached a mass M. And in this process, what happened? This wire made a V shape here. This distance is X. A mass M is attached at the center. And it goes down by X. Right? Assume X is much, much smaller. So I'm exaggerating the figure, but that X will be very, very small in millimeters. If length of the wire is 1 meter, it will barely sag by 1 millimeter. Assume X is much, much less than L. Find X. So when someone says X is much, much lesser than L, you can use the binomial approximation. Gravity is there. Is the question clear? When you attach the mass M at the center, it goes down by X. So find X in terms of L, A, Y. X is much, much smaller. So how we do this? Let's see. You'll get a cube root ray. See. So when the wire becomes like this, this length is x, this is L by 2, this is L by 2, let this be theta. So when this block is M here, this is tension T, this is tension T, this angle is 90 minus theta. So from here we get 2T cos 90 minus theta is equal to mg. So we get T is equal to mg by 2 sine theta. Now, since x is very, very small, for small theta, you can approximate sine theta is equal to tan theta, which is x by L by 2. So this guy becomes mg L by 4x. That's your tension in terms of x, right? And what is the elongation here? Here, the elongation in the wire will be the hypotenuse. So this length minus the initial horizontal length, isn't it? How much is that? That will be root over L square by 4 plus x square, that is your hypotenuse, into 2 times minus L. Agreed? The total hypotenuse minus L will give you the elongation. Take out L by 4 common, you will get 2 L by 2, 1 plus 4x square by L square whole to the power of half. We can use binomial approximation. This will be L into 1 plus 2x square by L square. LL will cancel. You end up with 2x square by L. That's your elongation. Hope everyone remembers the binomial approximation. 1 plus x whole power n can be written as 1 plus nx. There, I got my elongation in terms of x. I got tension in terms of x. So elongation, Young's modulus y is equal to tension length by AE. So tension is mgl by 4x, length L. This is area, and this is 2x square by L. So we have x cube is equal to mg L cube by 8ay. Therefore, x is equal to mg by 8ay whole to the power of 1 by 3 into L. Check. So the main idea here is get tension in terms of x and get elongation in terms of x. So you just substitute everything in that and you'll get it. Kind of a standard problem. You should definitely know how to do this. Have a look at this. Clear? Next one. We have a rope here hanging from the ceiling. Rope of density rho hanging from ceiling. Right? So we define something called a breaking stress. Breaking stress B. So what it tells you is the maximum stress the metal can withstand before it breaks. Right? So if you see breaking stress doesn't depend on the area of cross section, it is force per unit area. So it depends only on the nature of the material. And independent of area. Because if you have a thick area, you'll have more force. If you have less area, you'll have less force, but force per unit area is constant. So the question is, gravity is there. Find the maximum length so that the rope doesn't break. So if you just keep hanging a rope, bigger and bigger, at some point it will break due to its own weight. This is a problem that you face in tall buildings when you have a lift going from 0 to 100th floor. The weight of the wire itself will put so much stress on the system. It becomes economically difficult to put a one lift from 0 to 100. So people prefer like two lifts. Find max length so that rope doesn't break. Get it? Proper mains level question. Let's see. So which point is the weakest spot in this thing? The topmost point, isn't it? So we have maximum stress at the top. So at this point, tension T will be equal to mg. So tension will be mg, which is density, area, length into g. Stress will be tension by area, which is rho Lg. But this should be less than equal to B since you don't want it to break. So length must be less than equal to B by rho g. Easy. So it doesn't depend on the area. It does get cancelled out. Clear, everyone? Now, let's see a better version of this. Same thing, but imagine you have a shell. Radius r. T is the thickness of the shell. And r is much, much greater than T. So inside you filled it with a gas, pressure P. And let's say outside is vacuum. And B is the breaking stress. So this entire thing is a thin, it's a hollow shell with slight thickness. So the question is find the maximum pressure so that the shell doesn't break. So if you keep on pumping more and more air or more pressure, at some point the shell will just pop like a balloon. Find maximum pressure so that the shell doesn't crack. Breaking stress, I forgot to give. B is the breaking stress. Hmm. How do we approach this? Let's see. So just to give an idea, how do we start? Can you draw the FBD of the half shell? If you draw FBD of an half shell, this is what you will notice. So where is the tension acting? The tension is actually acting on this cross section, isn't it? This is your tension. And the gas inside is pushing it this way. So this gives you a force of pressure P into projected area. Hope you remember that. If a constant pressure is acting on a curved surface, the force is projected area. Therefore, we get tension is equal to P into pi r square. So when you take stress, what is stress? Force by area where the force is acting. Now, where is the area, on which area is this force acting? It's acting on this area. So your stress, right, or whatever force is actually acting on this. So the stress will be tension by area, which is P pi r square. The area will be 2 pi r into thickness. Is this making sense, everyone? So this area is the circumference into thickness. That is the reason I gave you r is much, much greater than t. Since the thickness is so small, you can treat it like a small thing. There's no need to take an element. T is very, very small. So why will you choose an element? Which element are you talking about? Now this should be less than equal to B so that it doesn't break. So B ka value will be less than equal to 2 BT by R. Now Purvaja, how will you choose an element?
Can we choose like a small patch and then
Okay.
the
कर सकते हो, but वही problem होगा ना, when you take a small patch, the tension is now acting in all directions. But when you take a half sphere, na, all will be in the same direction. It is easy to add up. Technically, you should get the same answer.
yes,
Hmm.
but उसमें
Meaning वही है ना,
डबल इंटीग्रेशन लगेगा ना तो
ये double integration का problem ही नहीं है. Problem is how will I take these angles actually? Meaning see, but this full sphere, if you take this piece, can you see how the tensions are? No, tensions are like this.
हाँ ठीक है हाँ I got
I
it.
don't know the angle, I don't know the radius. Becomes a problem. Half is always better. Is this clear, everyone? Right, Daksha, you got that. Vihan, Vignajit, clear with this? Surya, Nikhil, Parth. Next one. So that's on a breaking stress. This is an important question. Standard model came multiple times. We have a smooth floor. You placed a rod on it. Mass M, length L, area A, Young's modulus Y, alpha is the quotient of linear expansion. Find stress and strain when temperature increases by delta T. Let's get this. Let's see. So the first thing you need to ask yourself, so when the temperature is T, the length of the rod was L. Then the length of the rod became L into 1 plus alpha delta T when the temperature was T plus delta T. That means the reason why you expanded is because the molecule started vibrating more and they needed more space. This is your new natural length. Remember this? L into 1 plus alpha delta T is the new natural length. And what is the final length here? This is also the final length. Now, the problem here is delta L in thermodynamics, thermal expansion, and delta L in elasticity are not same. Delta L in elasticity is what? The change in length, that is L final minus L natural length. It is not your initial length. In this case, it is 0. The body will say, at this temperature, I was supposed to be L into 1 plus alpha delta T, and I'm L into 1 plus alpha delta T. So there's no problem for me. You're getting the difference? Whereas in thermal expansion, delta L is the change in length because of temperature. Like I gave you this example last time, think of like this. Suppose if I catch your cheeks and pull them, does it hurt? It hurts. Why? Because when I'm stretching your cheeks, that is not your natural length, your body hurts. But imagine you eat a lot of food and you become fat automatically on your own, and your cheeks have become bigger. Does it hurt? Now, in both the cases, cheeks have become bigger, but in the second case, it doesn't hurt because that happened naturally. You're getting the difference. So in this case, the reason the rod length increased is because of the temperature, and that happened internally. The molecules got pushed off. So it happened naturally. So there is no extra deformation or something. The rod will not feel I got deformed. So from here, the strain will be delta L by, remember, this is L natural length. In this case, it is 0 by L into 1 plus alpha delta T, which is 0. And we know stress is nothing but Young's modulus into strain. That is also 0. So the rod will feel there is no stress. Is this clear, everyone? Let me give you one more question like this. I think that will make things more clear. So when does it create stress then? All clear with this? So be careful. So delta L, if I have to write a statement, delta L in thermal expansion and elasticity are not same. Next question will make things more clear. Similar question, but this time, let's say we got a wall. Let's say we have a rough wall, mu and mu. And the rod got stuck between the walls. Young's modulus, area, length L, alpha, mass M. Gravity is there. So a rod is loosely fitted between the walls. Right. So the question is, find the change in temperature so that the rod does not slide. If you increase the temperature to a certain extent, the rod will push the wall and the friction will balance the weight. Find the change in temperature so that rod does not slide. Let's get this. Now, this and the previous one, they would be related to each other. When you see both the problems together, I think you will get a better idea. Now, if you ask the rod, what will the rod say? Again, ask yourself. The rod will say, if these walls are not there, see, it is always like that. If the walls are not there, I would have been L into 1 plus alpha delta t. So the natural length is L into 1 plus alpha delta t. But because of the wall, the rod didn't expand. Or should I say due to wall, the length of the rod remained L. What will the rod think? The rod feels it got compressed. You're getting it? Now the rod will feel I'm supposed to be this much, but I'm only L. Got compressed by L alpha delta t. Think of like this. Imagine your shirt ka size is M. You wore the shirt, you're comfortable, all great. And then for 2-3 months, you started eating a lot and your shirt ka size became L. Now, if you wear the same shirt, will it feel comfortable? Why doesn't it feel comfortable? Because now your natural shirt size has become L, isn't it? You're getting the problem here is comparing with the old self is a problem. You should always compare at this point of time, what is my natural size? Your natural size is not M anymore, it was L. You're getting it? So when you increase the temperature, the new natural size is supposed to be L into 1 plus alpha delta T. But due to the walls, you didn't let me expand, right? So this actually generates a stress. So now when you write the strain delta L by L, so here delta L will be L alpha delta T. When you apply the formula here, we get Y. So let's say the forces are normal reaction. Normal reaction. This is friction, and this is mg. So here the tension in the rod is N only. So when you apply the formula Y is equal to tension L by AE, we get N. This length will become L into 1 plus alpha delta T. That's your natural length. By A, E is L alpha delta T. So from here we get N is equal to Y A L alpha delta T by L into 1 plus alpha delta T. Since alpha delta T is very, very small, we neglect this term. Again, remember, compared to 1, alpha delta T is small. Then this guy becomes by A alpha delta T. And there we know for this to be in equilibrium, 2 times friction will be equal to mg. Therefore, friction must be equal to mg by 2. But I know friction must be less than or equal to mu into n since it is not slipping. So this guy would be mg by 2, and the normal reaction is mu y a alpha delta t. Therefore, the change in temperature must be greater than or equal to mg by 2 mu a y alpha. It should have at least this much change in temperature. So this actually creates stress in the material. Therefore, the rod is under stress. Now, for a person who is seeing from outside, it will feel like you are previously L, now it is also L, so you didn't change. That is not how you compare. What will you do with binomial approximation here?
Sir, 1 plus alpha delta t becomes 1 minus alpha delta t.
And then go ahead, and then just don't say and stop then.
Okay. Yes.
Think till the end. Just don't get 1 point and think like you figured out something. Go till the end. Examiner who will come and tell you all these things. So rod is under stress due to the temperature. So we call this thing thermal stress. It's like, a person crying, "Arey boss, my shirt size used to be M, now it became, when I wear the same shirt, it is not fitting." You're crying the wrong way. It doesn't make sense anymore. Your natural size has become L. This is called thermal stress. And this can actually have a pretty huge forces, right? You can see this thing, on highways also, when they build these flyovers, you'll observe they keep small gaps between section to section. During summers when they expand, right, that puts a lot of stress on the flyover if you don't leave space. Happens with railway tracks also. So railway tracks, what they do, they bolt these tracks, onto this. Ever seen that railway track, man? They keep that white cement color thing, they're concrete ones. So these things keep them, section by section from elongating. Unfortunately, sometimes if you don't put them properly, don't apply enough stress, things can go pretty bad. This is what can happen to railway tracks. Can you see how the entire track got bent? This is called buckling. So due to extreme heat, sometimes the thing will just not happen and this will buckle. So these stresses, right, thermal stresses can be pretty large. Next time, observe when they're installing your internet cable wires or something, the person who's installing the wire will keep the wire like this. He will make 1 or 2 loops and then he'll make the wire. Kabhi dekha? They'll always make 1 or 2 loops. Because during winters, when the temperature drops, the wire will contract. So if you make the wire exactly like this from here to here, the wire will be under stress and there's a chance the wire will crack. So you leave some extra wire here for that compression during winters. So few things. So you have to be careful. It doesn't look like much, but when the length of the wire is 200, 300 meters, right? Even that 1 or 2 centimeters ka compression will put a lot of stress on that. Any doubts on this? I hope A and B. Now these two columns are clear now. Now it made sense, right? So if you just leave it open, there's no stress, but you put it between a wall, there's a stress. It's like meaning think of a case like this. I put you between two walls. You're comfortably fitting between the walls. Now I keep feeding you every day, feed you, feed you, feed you, feed you, and you'll become fat. What will happen? That the same position will start feeling very uncomfortable, isn't it? You feel like the walls are compressing you. That's what is happening here. Clear? Now let's see a better variation of this. We have two walls here. We have a cylinder here. We have another cylinder here. This is Y1, A1, L1, alpha 1, Y2, A2, L2, alpha 2. This is the interface. This is the top view, so there's no gravity, nothing. You kept them like this, they're loosely fitted. Now, if you increase the temperature, what will happen? Both the rods will push each other. Find the distance moved by interface when temperature changes by delta T. Find the distance moved by interface when temperature changes by delta T. Let's get this. How do we do? This is a good one. Take a minute or two, think about it. This would be a proper advanced question. Maybe a more than one choice. Let me ask a simpler question. So when the temperature changes by delta T, now let's say it's a proper main cell question, there are the four options. Rod 1, rod 2, okay? Which of the following statements are true? Rod 1 and rod 2 both are compressed. Rod 1, rod 2 both are elongated. Rod 1 is compressed, rod 2 is elongated. Rod 1 is elongated, rod 2 is compressed. ऐसा four options होगा. In this, which one are wrong? Both compressed and both elongated, right? Now, let's see. Now, listen carefully. The main important thing is the diagram. If you got the diagram, you'll get this question. Let's say after increasing the temperature, this is the picture. It has become like this. Meaning the interface has moved here. So from this position till here, this distance is x. So x is the distance moved by the interface. Now listen to this thing. Whenever you're looking at elongation, the mistake is, I told you, you should not look from the initial, you should look from the natural length. Now, if you ask the left rod, if the right rod is not there, what would have happened to you? What will the left rod say? If the right rod is not there, I would have been this much. Agreed? And how much is that? From this initial position, I would have been L1 alpha 1 delta T. Agreed? But because of the right rod, finally, I had to settle down here. That means I got compressed by this much amount. You're getting what the left rod is trying to say? I was supposed to be L1 alpha 1 delta TT more, but because of this right rod, I lost what I got elongated, plus I also got compressed. So this will be E1, which is L1 alpha 1 delta T plus X. So the left rod got compressed. You're getting? Whenever you're saying compression and elongation, they should be measured from the new natural length, isn't it? You would have been like this, but you're like this. So you should be measured from this position. Is this making sense, everyone? Similarly, if the left rod is not there, what would the right rod do? If the left was not there, the right also would have been expanded like this. So this will say, I would have been L2 alpha 2 delta T, but because of the left rod, it did push me a bit. I had to settle down here. This was X, so this part got compressed. Both the rods are compressed, which is L2 alpha delta T minus X. So the mistake what people do now, you think when you're punching someone, you're hurting the other person. You're forgetting even your hand gets damaged. If you really hit someone on their skull or something, or their jawbone, they might get hurt, but in return, you damage your hand also. So even though the right rod looks like very strong and pushing, what you're forgetting is the left rod did actually resist and fought back. This left rod would have been till here. Because of that resistance, you got compressed by this amount. Is this picture making sense, everyone? If I ask you a question like this, we have a strong army and we have a weak army. Both the armies fought a war and the strong army won the war. After the war got over, which army became strong or which army became weak? Don't both the armies become weak? No matter how strong you are during the war, you must have lost some people, right? You did lose some resources. You did become weak, even though you won the war. So something of that sort. Is this making sense, everyone? So what is same in both the rods? Same tension. Why? The interface is at rest. Since interface is at rest, they should have same tension. And we know the formula, tension is equal to YA by YE by L. So this will be Y1, A1, E1 by L1 must be equal to Y2, A2, E2 by L2. The most common mistake what people do, they always try to measure it from the initial length. Don't do that. You should always measure it from the new natural length. So if you substitute here, this will be Y1, A1 by L1, L1 alpha delta T plus X, Y2, A2 by delta T. This will be L2 alpha delta T minus X. So bring X to this side. This will be Y2, A2 alpha 2 minus Y1, A1 alpha 1 delta T by Y2, A2 by L2 plus Y1, A1 by L1. Check. It's a pretty good answer. So how do we know which side dominates? It depends on the product of YA and alpha. Whoever has YA alpha ka value biggest, that guy is the strongest. Is this clear, everyone? Check it out. Any doubts on this? Clear? All clear with this? So that is a bit about elongation and stuff. So next class, we see today we didn't use any integration or anything. So next class when we catch up, we will continue from here. We will be having more more tougher problems, more integration based problems. They're not tough, but like I keep saying, if you know how to find tension, you'll be able to solve most of them. So next time when we catch up, we will continue with energy, and then we will see some integration based problems, and then we will also see the different properties of material and stuff and all. Okay, so with that, we'll wrap up for that day. So we'll catch up again on next Tuesday at 5:30 as usual, and we do have a meeting tomorrow also, so you can attend in your respective groups, right? And the test is online till Saturday, so make sure to give. So okay, with that, we'll wrap up for that day. So any doubts, anything you can stay back and ask, also free to leave. So take care, stay safe. See you on Tuesday at 5.